Reaching the outer solar system requires an immense amount of kinetic energy. To get a probe to a destination as distant as Neptune, we have to launch it at speeds exceeding 8 kilometers per second. But arriving is only half the physics problem. To keep that probe from flying straight past the planet, you have to slam on the brakes. Traditionally, that means packing thousands of pounds of heavy, volatile chemical fuel just to slow down and enter a stable orbit. That fuel dictates the entire lifespan of the mission. Once the thrusters run dry and the onboard nuclear batteries fade, the probe becomes a dead piece of metal drifting in the dark. There is an alternative to carrying tons of combustible liquid. Instead of firing a rocket engine, a spacecraft can unspool a 50-kilometer ribbon made of carbon nanotubes directly into the vacuum. This ribbon allows the spacecraft to interact with the planet's magnetic field to change its velocity. It offers a path to exploring deep space using replenishable electrical power rather than a finite supply of chemical propellant. This diagram illustrates the primary challenge at Neptune. Its magnetic field is remarkably weak. Because the field lines are spread so far apart, a tether must be incredibly long to cut across enough of them to generate significant electrical pressure, or voltage. But voltage is only part of the equation. To actually power a spacecraft, you need a high volume of current. By widening the tether into a flat multi-strand ribbon, you create a massive surface area that can scoop up a higher volume of electrons from the surrounding space. This geometry also ensures the mission survives the hazards of deep space. A single 50-kilometer wire is a massive target for space debris. But in a multi-strand mesh, if a micrometeorite severs a strand, the electrical current simply reroutes where the crosslinks. This design solves the mass-to-power ratio for long-duration missions. It functions as a resilient, wide-path motor that turns the spacecraft into a highly efficient generator. There is a structural paradox here. A single wire hanging in space is an open circuit. There is no return path for the electricity. Electrons should pile up at one end, creating a voltage pushback that would stop the flow almost instantly. The system works because the space surrounding the planet is not a total vacuum. It is a plasma lake of charged ions and electrons. This plasma acts as an invisible return wire, completing the circuit between the two ends of the tether. The ribbon acts as an anode, physically scooping electrons from this thin plasma gas and funneling them down into the spacecraft's main battery bank to be stored as chemical energy. To keep the circuit moving, the spacecraft uses a hollow cathode. This device spits those electrons back out into the vacuum, preventing a negative charge from building up on the ship and clogging the flow. By utilizing the planetary ionosphere as a bridge, the spacecraft turns the environment into a continuous electrical loop, keeping the systems powered as long as the tether remains in the field. Harvesting this electricity comes at the cost of orbital speed. As the tether pulls electrons from the plasma, the magnetic field pushes back against the ship. This is the Lorentz force, creating a magnetic drag that fills the batteries while lowering the spacecraft's altitude. This drag is exactly how the probe survives arrival. By dipping into the strongest parts of the magnetic field, the ship can shed its high velocity and successfully capture into Neptune's orbit without using a single drop of fuel. To maintain its orbit, the ship enters motor mode. It pumps its stored battery power back up the ribbon in the opposite direction. The magnetic field now pushes the spacecraft forward, providing the thrust needed to climb back to a higher altitude. Alternating between charging drag and battery-powered thrust creates a slinky orbit. This cycle allows the spacecraft to maintain its position around a planet for decades. This precise control allows the spacecraft to eventually match the speed of Neptune's moon Triton, establishing a stable, hovering orbit directly above its active cryovolcanoes. Because the probe relies on renewable planetary energy, it's not limited by a ticking fuel clock. It can loiter and observe these geological targets for years, waiting for the perfect moment to capture a plume eruption. Without the need for thousands of pounds of chemical propellant, engineers can fill the spacecraft with massive scientific payloads, including high-powered radar to see through ice and sub-probes to taste the moon's geysers. The gas giants are surrounded by massive, spinning rivers of untapped electromagnetic energy. This tower has always been there, moving through the ionosphere of every magnetic world. The future of deep space exploration does not require us to bring all of our energy with us. We only need to drop a ribbon into the current.